Multiple virtual storage, more commonly called MVS, was the most commonly used operating system on the System/370 and System/390 IBM mainframe computers. It was developed by IBM, but is unrelated to IBM's other mainframe operating systems, for example, VSE, VM, TPF. First released in 1974, MVS was extended by Program Products with new names multiple times, first to MVS SE, next to MVS SP version 1, next to MVS XA, next to MVS ESA, next to OS/390 and finally to ZOS. IBM added Unix support in MVS SPV 4.3 and has obtained POSIX and Unix certifications at several different levels. The MVS core remains fundamentally the same operating system. By design, programs written for MVS run on ZOS without modification. At first IBM described MVS as simply a new release of OS/VS2, but it was, in fact, a major rewrite. OS/VS2 Release 1 was an upgrade of OS/360 MVT that retained most of the original code and, like MVT, was mainly written in assembly language. The MVS core was almost entirely written in Assembler XF, although a few modules were written in PLS, but not the performance-sensitive ones, in particular not the input-output supervisor. IBM's use of OS/VS2 emphasized upwards compatibility. Application programs that ran under MVT did not even need recompiling to run under MVS. The same job control language files could be used unchanged. Utilities and other non-core facilities like TSO ran unchanged. IBM and users almost unanimously called the new system MVS from the start, and IBM continued to use the term MVS in the naming of later major versions such as MVS XA. Evolution of MVS. OS/360 MFT provided multitasking. Several memory partitions, each of a fixed size, was set up when the operating system was installed and when the operator redefined them. For example, there could be a small partition, two medium partitions, and a large partition. If there were two large programs ready to run, one would have to wait until the other finished and vacated the large partition. OS/360 MVT was an enhancement that further refined memory use. Instead of using fixed-size memory partitions, MVT allocated memory to regions for job steps as needed, provided enough contiguous physical memory was available. This was a significant advance over MFT's memory management, but had some weaknesses. If a job allocated memory dynamically, the programmers had to estimate the job's maximum memory requirement and predefine it for MVT. A job step that contained a mix of small and large programs wasted memory while the small programs ran. Most seriously, memory could become fragmented, that is, the memory not used by current jobs could be divided into uselessly small chunks between the areas used by current jobs, and the only remedy was to wait some current jobs finished before starting any new ones. In the early 1970s IBM sought to mitigate these difficulties by introducing virtual memory, which allowed programs to request address spaces larger than physical memory. The original implementations had a single virtual address space, shared by all jobs. OS/VS1 was OS/360 MFT within a single virtual address space. OS/VS2 SVS was OS/360 MVT within a single virtual address space. So OS/VS1 and SVS in principle had the same disadvantages as MFT and MVT, but the impacts were less severe because jobs could request much larger address spaces and the requests came out of a 16 MB pool even if physical storage was smaller. In the mid-1970s IBM introduced MVS, which not only supported virtual storage that was larger than the available real storage, as did SVS, but also allowed an indefinite number of applications to run in different address spaces. Two concurrent programs might try to access the same virtual memory address, but the virtual memory system redirected these requests to different areas of physical memory. Each of these address spaces consisted of three areas: an operating system, an application area unique for each application, and a shared virtual area used for various purposes, including inter-job communication. IBM promised that application areas would always be at least 8 megabytes. This made MVS the perfect solution for business problems that resulted from the need to run more applications. MVS maximized processing potential by providing multiprogramming and multiprocessing capabilities. Like its MVT and OSVS2 SVS predecessors, MVS supported multiprogramming. Program instructions and associated data are scheduled by a control program and given processing cycles. Unlike a single programming operating system, these systems maximize the use of the processing potential by dividing processing cycles among the instructions associated with several different concurrently running programs. This way, the control program does not have to wait for the I/O operation to complete before proceeding. By executing the instructions for multiple programs, the computer is able to switch back and forth between active and inactive programs. Early editions of MVS were among the first of the IBM OS series to support multiprocessor configurations, though the M65MP variant of OS/360 running on 360 models 65 and 67 had provided limited multiprocessor support. The 360 model 67 had also hosted the multiprocessor-capable TSS/360, MTS and CP67 operating systems. Because multiprocessing systems can execute instructions simultaneously, they offer greater processing power than single processing system. As a result, MVS was able to address the business problems brought on by the need to process large amounts of data. Multiprocessing systems are either loosely coupled, which means that each computer has access to a common workload, or tightly coupled, which means that the computers share the same real storage and are controlled by a single copy of the operating system. MVS retained both the loosely coupled multiprocessing of attached support processor and the tightly coupled multiprocessing of OS/360 Model 65 multiprocessing. In tightly coupled systems, two CPUs shared concurrent access to the same memory and peripherals, providing greater processing power and a degree of graceful degradation if one CPU failed. In loosely coupled configurations, each of a group of processors had its own memory and operating system but shared peripherals, and the operating system component JES3 allowed managing the whole group from one console. This provided greater resilience and let operators decide which processor should run which jobs from a central job queue. MVS JES3 gave users the opportunity to network together two or more data processing systems via shared disks and channel-to-channel adapters. This capability eventually became available to JES2 users as multi-access spool. MVS originally supported 24-bit addressing. As the underlying hardware progressed, it supported 31-bit and now 64-bit addressing. The most significant motives for the rapid upgrade to 31-bit addressing were the growth of large transaction processing networks, mostly controlled by CICS, which ran in a single address spatial euro, and the DB2 relational database management system needed more than 8 megabytes of application address space to run efficiently. The main user interfaces to MVS are Job Control Language, which was originally designed for batch processing but from the 1970s onwards was also used to start and allocate resources to long-running interactive jobs such CICS. And TSO, the Interactive Time-Sharing Interface, which was mainly used to run development tools and a few end-user information systems. ISPF is a TSO application for users on 3270 family terminals, which allows the user to accomplish the same tasks as TSO's command line but in a menu and form-oriented manner, and with a full-screen editor and file browser. TSO's basic interface is command line, although facilities were added later for form-driven interfaces. MVS took a major step forward in fault tolerance, built on the earlier STAE facility, that IBM called software recovery. IBM decided to do this after years of practical real-world experience with MVT in the business world. System failures were now having major impacts on customer businesses, and IBM decided to take a major design jump, to assume that despite the very best software development and testing techniques, that problems will occur. This profound assumption was pivotal in adding great percentages of fault-tolerance code to the system and likely contributed to the system's success in tolerating software and hardware failures. Statistical information is hard to come by to prove the value of these design features, but IBM has, in many dimensions, enhanced these fault-tolerant software recovery and rapid problem resolution features over time. This design specified a hierarchy of error-handling programs, in system mode, called functional recovery routines, and in user mode, called ESTAE, that were invoked in case the system detected an error. Each recovery routine made the mainline function reinvocable, captured error diagnostic data sufficient to debug the causing problem, and either retried or percolated. Thus, with each error the system captured diagnostic data, and attempted to perform a repair and keep the system up. The worst thing possible was to take down a user address space in the case of unrepaired errors. Though it was an initial design point, it was not until the most recent MVS version, that recovery program was not only guaranteed its own recovery routine, but each recovery routine now has its own recovery routine. This recovery structure was embedded in the basic MVS control program, and programming facilities are available and used by application program developers and third-party developers. Practically, the MVS software recovery made problem debugging both easier and more difficult. Software recovery requires that programs leave tracks of where they are and what they are doing, thus facilitating debugging. But the fact that processing progresses despite an error can overwrite the tracks. Early date capture at the time of the error maximizes debugging, and facilities exist for the recovery routines to do this. IBM included additional criteria for a major software problem that required IBM's service. If a mainline component failed to initiate software recovery, that was considered a valid reportable failure. Also, if a recovery routine failed to collect significant diagnostic data such that the original problem was solvable by data collected by that recovery routine, IBM standards dictated that this fault was reportable and required repair. Thus, IBM standards, when rigorously applied, encouraged continuous improvement. IBM introduced an on-demand hypervisor, a major serviceability tool, called Dynamic Support System, in the first release of MVS. This facility could be invoked to initiate a session to create diagnostic procedures, or invoke already stored procedures. The procedures trapped special events, such as the loading of a program, device I/O, system procedure calls, and then triggered the activation of the previously defined procedures. These procedures, which could be invoked recursively, allowed for reading and writing of data, and alteration of instruction flow. Program event recording hardware was used. Due to the overhead of this tool, it was removed from customer-available MVS systems. Program event recording exploitation was performed by the enhancement of the diagnostic slip command with the introduction of the PEO support in SU64/65. Multiple copies of MVS could share the same machine if that machine was controlled by VM/370. In this case VM/370 was the real operating system, and regarded the guest operating systems as applications with unusually high privileges. As a result of later hardware enhancements, one instance of an operating system could also occupy a logical partition instead of an entire physical system. Multiple MVS instances can be organized and collectively administered in a structure called a systems complex or sysplex, introduced in September 1990. Instances interoperate through a software component called a cross-system coupling facility and a hardware component called a hardware coupling facility. Multiple sysplexes can be joined via standard network protocols such as IBM's proprietary systems network architecture or, more recently, via TCP/IP. The Z/OS operating system also has native support to execute POSIX and single Unix specification applications. The support began with MVS SPV 403, and IBM has obtained Unix 95 certification for Z/OS v102 and later. Files are properly called datasets in MVS. Names of those files are organized in catalogs that are VSAM files themselves. The native character encoding scheme of MVS and its peripherals is ABCDIC, but the TR instruction made it easy to translate to other 7 and 8-bit codes. Over time IBM added hardware-accelerated services to perform translation to and between larger codes, hardware-specific service for Unicode transforms and software support of, for example, ASCII, ISO IEC 8859, UTF-8, UTF-16, and UTF-32. The software translation services take source and destination code pages as inputs. MVS file system. Data set names are organized in a hierarchy whose levels are separated with dots, for example. Department O1 SYSTEM O1 FILE O1. Each level in the hierarchy can be up to 8 characters long. The total file name length is a maximum of 44 characters including dots. By convention, the components separated by the dots are used to organize files similarly to directories in other operating systems. For example, there were utility programs that performed similar functions to those of Windows Explorer, adding, renaming or deleting new elements and reporting all the contents of a specified element. However, unlike in many other systems, these levels are not usually actual directories but just a naming convention. TSO supports a default prefix for files, and RACF supports setting up access controls based on file name patterns, analogous to access controls on directories on other platforms. As with other members of the OS family, MVS datasets were record-oriented. MVS inherited 3 main types from its predecessors. Sequential datasets were normally read one record at a time from beginning to end. In BDAM datasets, the application program had to specify the physical location of the data it wanted to access. In ISAM datasets, a specified section of each record was defined as a key that could be used as a key to look up specific records. The key quite often consisted of multiple fields, but these had to be contiguous and in the right order. And key values had to be unique. Hence an IBM ISAM file could have only one key, equivalent to the primary key of a relational database table. ISAM could not support foreign keys. Sequential and ISAM datasets could store either fixed-length or variable-length records, and all types could occupy more than one disk volume. All of these are based on the VTOC disk structure. Early IBM database management systems used various combinations of ISAM and BDAM datasets, usually BDAM for the actual data storage and ISAM for indexes. In the early 1970s, IBM's virtual memory operating systems introduced a new file management component, VSAM, which provided similar facilities. Entry sequence datasets provided facilities similar to those of both sequential and BDAM datasets, since they could be read either from start to finish or directly by specifying an offset from the start. Key sequence datasets were a major upgrade from ISAM. They allowed secondary keys with non-unique values and keys formed by concatenating non-contiguous fields in any order. They greatly reduced the performance problems caused by overflow records in ISAM. And they greatly reduced the risk that a software or hardware failure in the middle of an index update might corrupt the index. These VSAM formats became the basis of IBM's database management systems, IMS versus and DB2, usually ESDS for the actual data storage and KSDS for indexes. VSAM also included a catalog component used for MVS master catalog. Partitioned datasets were sequential datasets subdivided into members that could be processed as sequential files in their own right. The most important use of PDS was for program libraries. System administrators used the main PDS as a way to allocate disk space to a project, and the project team then created and edited the members. Generation data groups were originally designed to support grandfather-father-son backup procedures. If a file was modified, the changed version became the new son, the previous son became the father, the previous father became the grandfather, and the previous grandfather was deleted. But one could set up GDGs with a lot more than 3 generations, and some applications used GDGs to collect data from several sources and feed the information to one program. Each collecting program created a new generation of the file, and the final program read the whole group as a single sequential file. Modern versions of MVS also support POSIX-compatible /file systems along with facilities for integrating the two file systems. That is, the OS can make an MVS dataset appear as a file to a POSIX program or subsystem. These newer file systems include Hierarchical File System and ZFS. Programs running on network-connected computers can use local data management interfaces to transparently create, manage, and access VSAM record-oriented files by using client-server products implemented according to distributed data management architecture. DDM is also the base architecture for the MVS DB2 server that implements distributed relational database architecture. History and modernity: MVS is now a part of ZOS. Older MVS releases are no longer supported by IBM, and since 2007 only 64-bit ZOS releases are supported. ZOS supports running older 24-bit and 31-bit MVS applications alongside 64-bit applications. MVS releases up to 3.8J were freely available, and it is now possible to run the MVS 3.8J release in mainframe emulators for free. MVS/370 MVS/370 is a generic term for all versions of the MVS operating system prior to MVS XA. The System/370 architecture, at the time MVS was released, supported only 24-bit virtual addresses, so the MVS/370 operating system architecture is based on a 24-bit address. Because of this 24-bit address length, programs running under MVS/370 are each given 16 megabytes of contiguous virtual storage. MVS XA, or Multiple Virtual Storage Extended Architecture, was a version of MVS that supported the 370XA architecture, which expanded addresses from 24 bits to 31 bits, providing a 2 GB addressable memory area. It also supported a 24-bit legacy addressing mode for older 24-bit applications. MVS ESA, MVS Enterprise System Architecture. Version of MVS, first introduced as MVS SP version 3 in February 1988. Replaced by renamed as OS/390 late 1995 and subsequently as ZOS. MVS ESA Open Edition, upgrade to version 4. Release 3 of MVS ESA announced February 1993 with support for POSIX and other standards. While the initial release only had National Institute of Standards and Technology certification for Federal Information Processing Standard 151 compliance, subsequent releases were certified at higher levels and by other organizations, for example X-Open and its successor, the Open Group. It included about 1 million new lines of code, which provide an API shell, utilities, and an extended user interface. Works with a hierarchical file system provided by DFSMS. The shell and utilities are based on Mortis-Kern's interopen products. Independent specialists reckon it was over 80% open systems compliant, more than most Unix systems. DCE2 support announced February 1994, and many application development tools in March 1995. Mid-1995 IBM started to stop referring to Open Edition as a separate entity, as all the open features became a standard part of vanilla MVS ESA SP version 5 Release 1. Under OS/390, it became Unix System Services, and has kept that name under ZOS. Closely related operating systems, Japanese mainframe manufacturers Fujitsu and Hitachi both repeatedly and illegally obtained IBM's MVS source code and internal documentation in one of the 20th century's most famous cases of industrial espionage. Fujitsu relied heavily on IBM's code in its MSP mainframe operating system, and likewise Hitachi did the same for its VOS3 operating system. MSP and VOS3 were heavily marketed in Japan, where they still hold a substantial share of the mainframe installed base, but also to some degree in other countries, notably Australia. Even IBM's bugs and documentation misspellings were faithfully copied. IBM cooperated with the U.S. Federal Bureau of Investigation in a sting operation, reluctantly supplying Fujitsu and Hitachi with proprietary MVS and mainframe hardware technologies during the course of multi-year investigations culminating in the early 1980s Euro investigations which implicated senior company managers and even some Japanese government officials. Amdahl, however, was not involved in Fujitsu's theft of IBM's intellectual property. Any communications from Amdahl to Fujitsu were through Amdahl-only specifications, which were scrupulously cleansed of any IBM IP or any references to IBM's IP. Subsequent to the investigations, IBM reached multi-million-dollar settlements with both Fujitsu and Hitachi, collecting substantial fractions of both companies' profits for many years. Reliable reports indicate that the settlements exceeded $500 million. The three companies have long since amicably agreed to many joint business ventures. For example, in 2002 IBM and Hitachi collaborated on developing the IBM Z800 mainframe model. Because of this historical copying, MSP and VOS3 are properly classified as forks of MVS, and many third-party software vendors with MVS-compatible products were able to produce MSP and VOS3-compatible versions with little or no modification. When IBM introduced its 64-bit Z architecture mainframes in the year 2000, IBM also introduced the 64-bit Z/OS operating system, the direct successor to OS/390 and MVS. Fujitsu and Hitachi opted not to license IBM's Z architecture for their quasi-MVS operating systems and hardware systems, and so MSP and VOS3, while still nominally supported by their vendors, maintain most of MVS's 1980s architectural limitations to the present day. Since Z/OS still supports MVS-era applications and technologies indeed, Z/OS still contains most of MVS's code, albeit greatly enhanced and improved over decades of evolutionary Euro applications running on MSP and VOS3 can move to Z/OS much more easily than to other operating systems. See also, Hercules OS/370, S/390, and Z-Series emulator capable of running MVS. Utility programs supplied with MVS operating systems, batch pipes is a batch job processing utility designed for the MVS ESA operating system, and all later incarnations are Euro OS/390 and Z/OS. Notes. References: Bob Ducharme, The Operating Systems Handbook, Part 06, MVS, Os vs2 MVS Overview. First edition. IBM. June 1978. GC 28-0984-0. IBM Corporation, Unix 95 inches. The Open Group. Retrieved October 7, 2015. Hoskins, Jim. Frank, Bob. Exploring IBM eServer Z-Series and S/390 servers, see why IBM's redesigned mainframe computer family has become more popular than ever. Maximum press pages 210 Euro 290. ISBN 1-885068-91-3. Introducing Open Edition MVS. First edition. IBM. December 1993. GC 23-3010-00. Open Edition MVS POSIX Conformance Document. First edition. IBM. February 1993. GC 23-3011-00. Open Edition MVS POSIX2 Conformance Document. First edition. IBM. December 1993. GC 23-3012-00. Alexander, Charles. Budari, Bob. Now, from the FBI, Japan Scum. Time. Malone, Michael S. Hitachi FBI. Tapes are released. The New York Times. Moriyankadagai, Reprogramming Japan, The High-Tech Crisis Under Communitarian Capitalism, pages 159. External links, IBM, Z/OS v1 or 11.0 MVS manuals, IBM, Z/OS v1 or 8.0 MVS manuals, MVS. The operating system that keeps the world going, MVS. A Long History, Functional Structure of IBM Virtual Storage Operating Systems Part 2, OSVS 2-2 Concepts and Philosophies by A. L. Scheer.